some trig teachers and some trig classes really put a lot of emphasis on the unit circle earlier than we're mentioning it. We're really not going to use the unit circle that way. What most classes use the unit circle for, we use our special table of values for. Okay, so, but there are some concepts that are related to the unit that we're starting now that I want to get from the unit circle. There's a couple of identities that we need, and there are there's a concept that we're going to use that's going to be relevant to vectors and writing complex numbers in polar form. There's a lot of things that we're going to kind of do today that we'll build on later. So I want to show you the unit circle today. It's just kind of a little transitional lesson. The goal of this lesson is to get a couple of identities from the unit circle. All right? This is the identities unit we're starting today. We'll take a test late next week. This is not a real long unit, so we'll have a test late next week on identities if we get there. We may not get there. I hope we get there because I'd like to give you a drop test grade this 9 weeks. If we get another test in, I can justify doing that. If we don't, then I can't. But that means we might have one the second 9 weeks, a drop test. So you just drop the test, just kind of goes away, your lowest test score. That's my goal, to get that done. Identities are very easy for some students and very difficult for others. There's a lot of memorization, so when I tell you to memorize something, it's a good idea to spend some time that day committing it to memory so you're not trying to memorize a bunch of stuff the night before the test. That's not going to go well for you if you do that. All right? So the unit circle is going to be important. The unit circle is built around the special right triangles. Don't write this down yet because I'm going to tell you what to write, when to write, and where to write it. Just everything's going to go on this page today. All right, so special right triangles, there's two of them here. This top one is which one? It's the 30, 60, 90, right? And what are the dimensions or the ratios, the sides of the 30, 60, 90 triangle? 1. The hypotenuse is 2. And this one is the square root of 3, right? And if we blew that triangle up and made it larger, we could just multiply all those values by 3, for example. So we could have 3, 6, and 3 square roots of 3 by multiplying by 3. Or we could divide them all, which is what we're going to do a little bit later. All right, in the other one, we have the 45, 45, 90 triangle. And what are the ratios of the sides of the 45, 45, 90 triangle? If these are 1, these are equal. The hypotenuse is the square root of 2 times whatever the legs are. So if the legs were 4, then the hypotenuse would be 4 times the square root of 2. Okay? Everybody okay with that? If the legs were 1/2, then the hypotenuse would be 1/2 times the square root of 2, or the square root of 2 over 2. All right, so that's the special right triangles, and we use the special right triangles plus our kind of imaginary triangle. Remember our imaginary triangle that we did in class? We did the 0 degree 90 90 0 90 90 triangle where this was 1, that was 1, and this was 0, and we use that to find the tangent of 0, the sine of 0, the cosine of 0, the sine of 90. Remember? Yes. Sine of 90 degrees is the opposite over the hypotenuse. Okay. The sine of 0 is 0 over 1. Yes, remember this. Y'all aren't paying attention. It's going to be important that you pay attention to these things. Okay. All right, so that was Elizabeth Johnson. All right. You're famous now. You're on YouTube, Elizabeth. All right, so we use these triangles to create our table of values. I'm sorry, this is a nice colored page on my iPad, but you guys can't see it on the projector. So our table of values was, so let's kind of review quickly how we did this, because this is still going to be our primary tool that we use for solving equations, and what some teachers choose to use the unit circle for, we use this table of values. But we used those three triangles to fill in the values of this table of values, and we looked for patterns, right? So let's remind ourselves what the patterns were. Our special angles are 0 degrees, 30 degrees, which is pi over 6, right? And 45 degrees, which is pi over 4. 60 degrees, which is pi over 3. And 90 degrees, which is pi over 2. And we have sine of our angle, cosine of our angle, and then tangent of the angle we fill in later using the sine and cosine. All right, so what was the pattern? Every denominator is 2. I want you to remember this. I want you to take this off to college with you. Any of you guys that are taking math classes beyond this table of values is extremely, extremely helpful. Cosine. All of the sines and cosines are over 2. Every numerator has a what? Square root, right? So we start with sine of 0 is 0. Okay? 0, 1, square root of 2, square root of 3, square root of 4. And we simplify what we can. Sine of 0 is 0, sine of 30 is 1/2, and this simplifies to be 1. And then the cosine just goes, instead of starting at 0, it's 4, 3, 2, 1, 0. And this is 1, this is 1/2, and this is 0. Okay, so we use this table of values in our trig test 2 material. We're going to use it again a lot in test 6 when we're solving trig equations. Okay, this is going to be our kind of a go-to chart for us. And then the tangent is the sine divided by cosine. So that's 0, 1 over the square root of 3. That's 1. That's the square root of 3 over 1, and this is undefined. Okay? Right? Y'all remember this? All right, so what we're going to do today is I'm going to show you a relationship between this table of values and the unit circle, which we kind of already done when we graphed. Remember we used the graph and we used this table and filled in that great point by point, do the trig graphs back in before. So, all right. Now this I want you to write on the bottom of your sheet. Bottom left and bottom right. Put one triangle on the left, one triangle on the right. Today we're talking about the unit circle. Why is it called the unit circle? Does anybody know? Anybody remember? Any of you trig students remember why we call it the unit circle? Do what? No, that's not it. We could talk about that, but that's not the correct interpretation of unit. By units here, we're not talking about degrees, radians, inches, feet. We're talking about the unit. In mathematics, the unit is 1. Okay? So the unit circle is a circle that has a radius of 1. That's why it's called the unit circle. The radius of the circle is 1. Okay? Now, so for us to use our special right triangles, we need our hypotenuses. Hypotenae? We'd have to ask Timothy Morris about that. We need our hypotenuses to be 1. Okay, so if I want the hypotenuse of the 30, 60, 90 triangle to be 1, what was it before? It was 2, right? So I'm dividing 2 by 2 to get 1. So if I divide the hypotenuse by 2, I need to divide the legs by 2. So this will be 1/2. And this will be square root of 3 over 2. I'm just taking the 1 square root of 3, 2 circle and divide all the sides by 2. I'm shrinking it by half. We could multiply it by 6 if we want to. Whatever you want to do, you can do to a circle. Where, in this case, we're doing a contraction instead of a dilation. If you go back to your geometry terms, we're contracting this circle. We're shrinking it. Triangle, not circle. All right? Now, if I want the hypotenuse of the 45, 90 triangle to be 1, and again, we're doing this because the unit circle has a radius of 1, then what was our other ratio that we had? We had 1, 1, and the square root of 2, right? So I'm dividing by the square root of 2 all the dimensions of the right triangle. So if we rationalize it, that means this is going to be the square root of 2 over 2, and this side will also be the square root of 2 over 2. 1 divided by the square root of 2 is the square root of 2 over 2. Right? I see some quizzical looks. 1 divided by the square root of 2, if you multiply top and bottom by the square root of 2, you get, to rationalize it, you get the square root of 2 over 2. So 1 divided by the square root of 2 is the same as the square root of 2 divided by 2. Those are equivalent fractions. Okay? So now we've got some triangles, and excuse me, you guys have these triangles drawn on the bottom of your page, so we can use these triangles in the unit circle, and here's what that's going to look like. Let's start with the fact that our radius is 1, right? This is a circle that has a radius value of 1, so you can write that somewhere kind of away from the circle. Our radius is equal to 1. This circle, so we can kind of, what that means is from here to here is 1. Don't draw this, by the way. I'm going to tell you what to draw and when to draw it. So that's 1. From there to there has a length of 1. That's the radius of that circle. Anywhere we draw a radius, its length is 1. Right? So we're going to drop some triangles in here. The radius of the triangles, the hypotenuse of all of our triangles will always be 1 because the radius of the circle is 1. All right, now that's going to help us label the points. What we want to do is label the points all the way around. So I want to label that point, that point, that point, that point, using rectangular coordinates. So I just need to know the x coordinate and the y coordinate of each of those points. That's our goal of what we're doing here. And now we'll make the application of what it all means in a minute. Okay, so take your straight edge that I gave you and draw triangle here. It's not letting me draw it the way I want to draw it. Okay. Now that's 30 degrees on the circle, which means that angle there is 30. What kind of triangle are we working with here? What kind of triangle are we working with here? 30, 60, 90, right? So I want to label this x and y coordinates of this point, right? So what's this x value going to be along here? We just drew these triangles on the bottom of your sheet there. What's that long leg of the 30, 60, 90 triangle when the hypotenuse is 1? Square root of 3 over 2, right? So this is the square root of 3 over 2. And the y value, the vertical side of the triangle, is 1/2, right? So the y value is 1/2. Okay? Does everybody see that? Any question about where those values are coming from? I need you to understand this. I don't want you to just write this down and try to memorize it. I need you to understand this. I don't want you to memorize the unit circle. I want you to memorize the table of values. Because the table of values, you'll see the way they are similar here in just a moment. All right, next little notch up there would be 45. So if we drew a 45-degree angle here, why my cursor is not wanting to calibrate correctly. Well, best I can do. This is a 45, 45, and again, the radius is 1. What did we say that the length of the legs was going to be? They both have a value of what? Square root of 2 over 2. So this x value, this side of the triangle is square root of 2 over 2. And this side of the triangle, my y coordinate is also the square root of 2 over 2. Okay? So y'all see where this is taking us now? What's the next triangle going to be? The next triangle is going to be a 60-degree angle, which is back to which of our special triangles? 30, 60, 90. And this is not letting me draw the triangle correctly. Of course, I didn't have any trouble earlier periods today when I wasn't recording. There we go. So this is the 30, 60, 90 triangle, except now the 60-degree angle is down here. The 30-degree angle is up top. So that's just going to reverse the x and y coordinates that we used for the 30-degree angle, right? My x coordinate is now 1/2, and the y coordinate is the square root of 3 over 2. Bryce, you okay? Logan, you okay? You good? Now we're almost done with all of the first quadrant. Well, that is all the first quadrant angles, but we missed our starting point and stopping point. So what are the coordinates of these 2 points? At 0 degrees, what are the coordinates of that point? X is equal to, our radius is what? 1. And y is 0, right? And then at 90 degrees, the coordinates of that point are going to be x is 0, y is 1. Okay? Now, go back to your table of values. All right, you've got it here, right? Does everybody see the sine line? The sine, right? Sine starts at what? Sine of 0 is 0, right? Y'all watching? Sine of 0 is 0. Sine of 30 degrees is 1/2 from your table of values, right? Sine of 45 degrees is square root of 2 over 2. Sine of 60 degrees is square root of 3 over 2. Sine of 90 degrees is the square root of 4 over 2, which is 1. Okay? And cosine of 0 degrees is 1. Cosine of 30 degrees is square root of 3 over 2. Cosine of 45 is the square root of 2 over 2. Cosine of 60 is 1/2, and the cosine of 90 is 0. So what can we say about these points? What does the y-coordinate of the point represent? The y-coordinate is the sine of the angle, right? And the x-coordinate is the cosine of the angle. So if we came in here and we just put a random point anywhere on the circle, let's put a point right here. That's theta degrees. The x-coordinate of that point is cosine of theta. The y-coordinate of that point is the sine of theta. I'm running out of room here. Cosine theta, sine theta. All right, y'all clear with that? So if I come up here to 80 degrees or 75 degrees, and I want to put a point right here at 75 degrees, if that's 75 degrees, a 75-degree angle down to there, this is 75 degrees. The coordinates at that point would be the cosine of 70 degrees and the sine of 70 degrees. You could literally take your calculator, cosine of 75 degrees, and that's going to be your x value for your coordinate. Sine of 75 degrees would be your y value of your coordinate. All right? So that's the significance. This fact right here is huge. So you need to pick a point somewhere on your unit circle where you've got some space and put theta degrees, cosine of theta, sine of theta. The x-coordinate is the cosine value. The y-coordinate is the sine value. That's the most important takeaway so far. Now, let's use these values that we found in the first quadrant to label all the other points around the circle. And this is going to go quickly because we don't need to spend a whole lot of time drawing every triangle. Let's come over here to 150 degrees. What are the coordinates of that point going to be? Just using what we have on the other side. What's the reference angle for 150? It's 30 degrees, right? So there is a relationship between 150 degrees and 30 degrees. You can kind of see it. See the dotted lines that are tying all those angles together? Those all have a reference angle of 30 degrees, right? So what's the difference between 150 degrees and 30 degrees? What's the difference? Do what? The cosine is going to be negative, which means the x-coordinate is negative, right? That's consistent, right? To the left of the axis. So this will be negative square root of 3 over 2. And this will be x is negative square root of 3 over 2. Y is still positive 1/2 because it's up. And you got to kind of remember ASTC is in play. So if the cosine is negative, that means the x-coordinates are negative, and they just kind of mirror their partners across the y-axis. So this one, 135 degrees, is going to be negative square root of 2 over 2 for cosine, positive square root of 2 over 2 for sine. 120 degrees is going to be negative 1/2 for cosine, square root of 3 over 2 for sine. Go with me? And then this point, 180 degrees, the x-coordinate is negative 1, the y-coordinate is 0. What does that tell us? Cosine of 180 degrees is negative 1. Sine of 180 degrees is 0. 210 degrees. We just keep going around. What angles is it tied to? See, these kind of this ties all 4 of these angles together. Those are all 30-degree reference angles. So the values are the same, just the signs change. And we've seen that already in our. So this is negative square root of 3 over 2 and negative 1/2, right? I need to slow down. And if you literally came in here and drew the 30, 60, 90 triangle and labeled the sides correctly with left and down being negative, you would see this. The 225 is negative square root of 2 over 2 for x. Negative square root of 2 over 2 for y. And then 240 is negative 1/2 for x, negative square root of 3 over 2 for y. That's the cosine and sine of that angle. And 270, what are the coordinates of that point? X is 0. Y is negative 1. Cosine of 270 is 0. Cosine of sine of 270 is negative 1. All right, so if we fill these on in, what else can we see? What's 300? 300 ties us to this point, right? So it's 1/2 and negative square root of 3 over 2. 315, that's my 45-degree reference angle. Square root of 2 over 2. X is positive in this quadrant. Y is negative. 330. X is positive. Y is negative. So this just kind of continues all the way around the circle, and it just goes forever and ever and ever, and just repeats. It's very monotonous. There's only two special triangles, right? 30, 60, 90, 45, 45, 90. So we put these two triangles wherever you put them and change the signs according to the quadrants. That's what you get. Okay, so let's talk a little bit about the circle, and then we're going to make some applications and be done. Who remembers what the equation of a circle is from Algebra 2? Do what?
Pi times diameter.
That's the circumference of a circle, pi times the diameter. That's good. Fox, you remember? Equation of a circle.
It's like y squared and x squared.
Yeah, x squared and x and y are both squared. The formula, don't write this down. Don't write this down. I'm going to tell you when and where to write it. The formula is x minus h squared plus y minus k squared equals the radius squared. That's a good formula to know for the ACT. It really is. Okay? Now, in this particular circle, the unit circle, the center is what? What's the center of this circle right there? It's 0, 0, isn't it? Right? So if h and k are both 0, then that we have x squared plus y squared equals, what's the radius? 1. 1 squared is 1. So the rectangular equation here that we're working, the rectangular coordinate equation of this circle is that. X squared plus y squared equals 1. Okay? And that means that if we take this circle, y'all go ahead and write this x squared plus y squared equals 1. Write it up on the top left-hand side of your graph. That's the equation of the unit circle. So top left corner up there, just write x squared plus y squared equals 1. Because if we take any point on the unit circle, any point, the rectangular coordinates of this point right here, x, y. If I were to draw a right triangle with that circle, the right triangle with this point, this is my x value, that's my y value, the hypotenuse is 1, right? What would the Pythagorean theorem give me on that triangle? X squared plus y squared equals 1 squared, which is 1. Right? So for every point on the circle, that's true, including this very important point right there. What's the x coordinate of that point? Cosine of theta. What's the y coordinate of that point? Sine of theta. And if I plug that equation or use that value with x squared plus y squared equals 1, then what do we get? We get cosine squared of theta plus sine squared of theta equals 1. Theta is any angle. Are y'all listening to me? That's a huge fact. And that's kind of why I wanted to do the unit circle today, so you can see that relationship that comes into play with x squared plus y squared equals r squared. And if r is 1, then we've got the unit circle, and we get this trig identity, cosine squared plus sine squared equals 1. All right, so let's kind of tie this up and finish up for the day. Let's look at some facts related to the unit circle. You can flip over on the back of your page and write these facts somewhere. What did we discover about the x coordinate of each of the points on the unit circle? The x-coordinate is the cosine of the angle. All right. Now, we could write that as x equals the cosine of theta. But that means that the x-coordinate of the points on the circle is the cosine of the angle. Now, these are specific to unit circles. If we change the radius of the circle to 5, then x would be equal to 5 times the cosine of theta. So a more general formula that we could use, and we will use when we start doing polar coordinates, is x equals the radius of the circle, or the magnitude of the vector, times the cosine of theta. X equals r cosine of theta. That's the general. But if the radius is 1, x equals the cosine of theta. All right, what do we learn about the y-coordinate of the y is equal to the sine of the angle. All right, so the trig, if we just wrote this in trig, y is equal to sine of theta. And when we get a little bit later, if we change the radius of the circle, or the magnitude of the vector, or the location of the complex number, it's going to be very repetitive. All these, y is equal to r, whatever the radius of the circle is, times the sine of theta. Those of you who are taking physics now, you see this a lot when you're doing your forces and things like that. This comes from the unit circle, or that's one way to show it. It's not the only way to show it. All right, what do we already know about the tangent of these angles? From our table of values, the tangent is equal to the sine divided by the cosine. So that means that the tangent of the angle is equal to y divided by x. Tan theta, tangent of the angle, is equal to y divided by x. Now, if we extend that, what is y equal to? What is y equal to? Previous fact. Sine of theta. And x is equal to the cosine of theta. Tangent is y divided by x, which is the sine of theta divided by the cosine of theta. Regardless of what the radius is, right? Because if you put r in both of these, if we're talking about any other circle, if you put an r there, then the r's cancel out, and it's just y divided by cosine of x. Now, another fact, and this is not going to make a whole lot of sense to you at this point, but I want to show it to you. I don't even want you to write this down. The angle that we're dealing with is always the inverse tangent of y divided by x. That's how you find your directional angle from just having a point. That's going to come into play at some point. Okay, all right, so that fact is there. We've already got that. And for each point x, y on the circle, we kind of incorporated this last point in with the previous one, sine divided by cosine. For each point x, y on the unit circle, x squared plus y squared equals 1. Right? That's the equation of the unit circle. So if we make our substitutions, what is x equal to? X is the cosine of the angle theta. So this would be cosine of theta squared plus the sine of theta squared equals 1. This identity right here is huge. This is called the Pythagorean identity. And it comes from this. Remember, I showed you that this was just the Pythagorean theorem for the unit circle. X squared plus y squared equals 1. And that means that the Pythagorean identity is the cosine squared plus the sine squared equals 1. We're going to use this identity tomorrow or the next day to come up with 6 other Pythagorean, or a total of 6 Pythagorean identities that you're going to have to, you ready for it? Memorize. Memorize this. This is huge. The sine squared of an angle plus the cosine squared of an angle is equal to 1. Okay? And that's it for today.